Okay, so it's great to be here. I'm Assaf. I'm a senior solutions architect in NVIDIA for the past 4 years or so. And I'm a multimodality senior solutions architect because I'm dealing with a variety of AI applications in all of the fields. But today I'm going to speak about LLMs, large language models. It's going to be a bit technical, but also I'll speak first about the history and the other things. And how to run them in production on GPUs and all the benefits that you can get from running what we can afford for you. So let's start with history. 2022, there was the explosion. ChatGPT was announced, 100 million users in just 2 months that started having fun with AI, with generative AI, and just experience it for the first time in their life. 2023 was the experimentation phase, where companies started to do POCs with generative AI, started to integrate it into their applications, using services like OpenAI and talking with the APIs, sending requests and receiving answers back. And today, 2024 and forward, we are in the production phase, where where companies actually set budget to integrate generative AI into their products, and it's part of the main core of the application itself. Now, what is generative AI? Generative AI is the ability to generate content using deep neural networks, using different inputs, could be text, audio, video, 3D, even proteins in the healthcare industry. And it's the ability to understand the patterns and the structure of the data in order to produce outputs. And these outputs are being produced using probability, using distribution. And what we eventually get is something which is called foundation model. Now, these neural networks are being trained in semi-supervised and unsupervised ways, which allow them to ingest an enormous amount of data. And they are today in very, very large weights. And LLM is part of the generative AI, where it generates the next token every time. Now, dealing with generative AI also includes challenges. 2 of the challenges are here. This is the first one, where we need to decide how and where to deploy the model. The first option is to use a managed generative AI service, just like OpenAI, where they expose an API to us. We can send the requests, they process the data, they run the model, they do everything, and we just receive the answer. It's the fast path to get started, but we also can't control the model. The infrastructure is limited, and the data is shared externally, so we can't really send any confidential data. The second option is to go with do-it-yourself deployment. In this case, we decide which model to use and to deploy it in our data center or in the cloud, but we manage everything. So we can run it anywhere, and we can use confidential data. But on the other hand, we need to take care of everything. We need to add custom code in order to expose the APIs, and we need to maintain everything in order for it to work. If we decide to choose a model that we want to fine-tune, we need to fine-tune the model, and so on. The next challenge is the trade-off, and especially in LLMs, between throughput and latency. Throughput stands for the number of successful operations per unit time, and it is measured by tokens per second. So how many tokens, how many words we were able to generate in one single time, in one single second. And we want this to be as high as possible. The second thing is latency. This is the delay before or between data transfers. And it is measured by time to first token, TTFT, and inter-token latency. TTFT should be under a few seconds or shorter. This is because if the user speaks with the chatbot, for example, we want him to receive an answer as fast as possible so it feels live. And ITL should be less than the human reading speed, because once the first token was ever generated, We want to always be ahead of the user when he starts reading. And there is a trade-off between the two, because we want to get high throughput and low latency. But if we will increase the throughput too much, the latency will also be increasing. One option to tackle it is to try different throughputs, try different parallel requests in order to find the sweet spot where we set a limit for the latency. And just as you can see here, we find that 50 concurrent requests can give us the optimal position. On the right, you can see the use of NVIDIA NIM, which I will talk about in the next slides, which improves both the throughput and the latency, both the TFT and the ITL. And we will discuss how. So NVIDIA NIM. NIM stands for NVIDIA Inference Microservices. And these are models optimized by NVIDIA and served as containers or Helm charts. So you can download them and deploy them anywhere you want. They provide industry standard APIs like OpenAI and LangChain. So if you're already using something like this, you can basically take and replace it with NIM. They support for custom models. There are some that are generic, some that are custom, depending on the model that we are using. And they optimize everything. To interact with NIM, to experience it, oh, by the way, I forgot to mention, in my slides, I will show QR codes that you can scan during the presentation and find the blog post about the specific slide that I'm presenting, so feel free to do it. So let's say that we want to experience with NIM. You can go to our catalog, which is build.nvidia.com. And this catalog shows all the models that we have, where you can choose and experience with straight away from the browser for free. You can send requests and receive answers. You can also prototype with them by writing your own code and generating some API in order to communicate with our catalog. And once you find that the NIM is good for you and the model works as you expect, you can download it and deploy it wherever you want. As I said before, there is a NIM for every domain. So for text, for example, we have Llama. It says 3.1, but it's already 3.2 and 3.3. For visual, SDXL. For, I don't know, speech, we have a Parquet. And more. They are always updating. Every time there is a new model released out there as open source, we take them and we optimize them. Let's look inside the NIM. Here in green, you can see the NIM container. And we'll start from the top. We have the client that communicates with the container via HTTP requests. So you send a request, like a prompt. It reaches inside the OpenAI compatible API or the LangChain, which is built on the FAST API and provide different endpoints. Then the LLM executor. This is the one which is in charge of the routing, of the tokenizing, of handling all the requests. He takes the request and sends it to one of the two runtimes. One is TensorRT LLM, which is our optimized runtime environment, if it's possible. And the second one is the VLLM1. You can take NIM and deploy it in every cloud, and there is explanation and documentation on it. Or you can use Kubernetes. And if you do so, you also need to use our NIM operator. And OK, and let's say that we decided that we chose a NIM. We saw that it's good, and we want to use it. The workflow here demonstrates this workflow. So first, we use Docker run in order to download the NIM container from our catalog. It is being pulled, and then it runs locally on your hardware. So it could be any GPU that you can think of. And based on the GPU and based on the number of GPUs, it will download the relevant model out of a list of profiles. If there is an optimized TensorRT LLM profile available, it will download the model and save it in the cache. And if not, there will be a graceful failure, and it will download the VLLM version. Once it is being downloaded, it will be saved in the cache environment, and then every time that you run the container again, it will be loaded from there, so you don't need to re-download it. And there are different profiles. For example, for the Llama 3 8B model, you can see that there are different profiles for every combination that exists. So we in NVIDIA did the hard work for you. We created all the models available. So if you choose a GPU architecture of H100 with 2 GPUs, it will take the latency profile with the relevant precision that you want. It all happens automatically because it recognizes what you run at, but you can also list it and you can choose it manually if you prefer. Here you can also see that it supports LoRa, which I will talk about a bit later on. This is for the Llama 3 8B, and this is for the Llama 3 70B. So you can see that we have different profiles and different models for every model that we release in NIM. And we do it because every GPU architecture is different, and the use of 2 GPUs or 4 GPUs is different, and we want you to get the maximum that you can. This will be your starting point. Now, here, if you can please play the demo. There is a short demo, about 4 minutes long, that will just show everything that I just said. Let's see if it works.
Looking to get your hands on the latest generative AI models accelerated by NVIDIA? Today, we're going to show you how easy it is to try out and deploy the latest AI models for high-performance GPU-accelerated inferencing, privately and securely on your own infrastructure using a single command. First, we can find out what models are available on the NVIDIA API catalog at build.nvidia.com. There are several models available across a bunch of different domains, like Stable Diffusion and ESM Fold, but the one we'll be using today is Llama 3. We can quickly test out the model right here on our web browser and see how it performs. For example, let's try asking the model to write a limerick on GPU computing. And here's the resulting output. We can also test out the model programmatically with the hosted APIs by generating an API key and using the sample code snippets here. To deploy a NIM ourselves, we can move over to the Docker tab on this page. That'll give us the instructions for pulling the NIM container and running it in our own environment. Note that in order to download NIM, you'll need to sign up for an account. You can sign up with a business email for access to NIM through an NVIDIA AI Enterprise license, or a personal email for free access to NIM through the NVIDIA Developer Program. You can choose the best option for your needs. Let's go over to the command line and see what the deployment process looks like. The first thing we'll need to do is log into the NVIDIA Container Registry. To do this, we'll need to have Docker Engine and the Docker command line tool pre-installed. We can type in docker login followed by nvcr.io for NVIDIA Container Registry. For the username, we'll use $OAuth token, and for the password, we'll paste in the API key that we got from the API catalog webpage. Now, we're authenticated with the container registry. Our next step will be to create an environment variable called ngc API key in our session that holds the same API key value. I've already done this, so I'll skip that step here. And then to get things running, we just need to input the single docker run command, which I can paste in here. This will pull the container image, download the necessary model weights, and deploy the NIM microservice that we can use as a local API endpoint. There's a couple of flags here that I think are useful to take a look at. The first is GPUs all. This is telling Docker to expose all of the GPUs to the running container. In the next one, we're letting Docker know to expose the API key environment variable that we set previously. Here, we're mounting this path to opt.nim.cache directory within the NIM container. This is where NIM will download and store the model weights so that they don't have to be re-downloaded on future deployments. Next, we're specifying that the NIM should run as our local user. Finally, here we're exposing the port 8000 from inside the container to the outside. That's the main port where we'll be sending all of our HTTP requests in order to interact with the running NIM. And the last bit here is the actual container image, the image path and the tag. Note here that when we deploy NIM, we include the name of the model in the image path itself. So in this case, we'll be deploying the Llama 3 8B model, and if we were going to deploy the Llama 3 70B model, or any other model, it'd be a different image path. And we can scroll then to the end of this log here, and see that this last message is telling us that our service is running on port 8000, and that it's ready to listen for requests. To confirm that the service is ready, I can move over to another terminal and send this health ready request with curl, and I see the response come back with the message that the service is ready. So now that the NIM is ready, let's try sending a request. I'll try asking for a limerick again by pasting in this command to my terminal. And we quickly get back a response with a lovely little poem, just like we saw on the web interface.
Okay.
And that's a wrap. We've deployed one of the latest community AI models for secure, high-performance inferencing on our own NVIDIA accelerated infrastructure. Looking to run more?
Okay, so very simple, few clicks, really 5 minutes, and you got a running model as long as you have the relevant hardware. You can scan the QR code at the top to reach a blog post about it. Performance. Let's look at performance. Mistral 8.7b and Mistral 8 2020-22b without NIM and with NIM. Look at the difference. 4 times better throughput and 3 times better throughput in the other model. It's just crazy how optimized it is. Now I want to look inside the features that NIM can offer you. Starting from TensorRT LLM and Triton, which are 2 libraries already integrated with NIM. TensorRT LLM is our library for optimizing large language models, and it is built on the TensorRT, which is already known by itself. And it provides things like custom kernels, in-flight batching, KV caching, and more. And we have Triton. This is our inference server. This is the one which is in charge of loading the model, creating the model repository, and serving it. And just by running NIM, you have the model running, the repository existing, and the server which can accept the different requests. So TensorRT LLM includes a few features, starting from in-flight batching, which is also known as continuous batching, which is an improvement comparing to the regular static batching. The static batching, when you send a request, when you send a batch of requests, need to wait for the longest request to finish before proceeding to the next batch. Like we can see here, there are 4 requests in one batch, and not all of them are the same. Think about a chatbot where one person asks a very short question and another one asks him to summarize an entire page. So in this case, we are wasting a lot of time. In-flight batching, once a request was finished processing, it will already put inside another request while the others are still in flight. This is part of the batch manager component, by the way. The next thing is KV caching. KV stands for keys and values. These are 2 matrices that are being computed in the pre-fill phase. And then in the decode phase, they are being used in order to generate token after token. Now, these 2 matrices don't need to be recomputed every time, because once we computed them, it's basically matrix by matrix multiplication. It's good enough. So what we do is that we store them in the cache memory, and then every time, in every step, a new token is being generated, we actually expand these 2 matrices and just add a small vector to it and use it for the next step forward. I'm sorry for the colors, it should be a little bit different, but it's good enough. Now, what NIM does, it's not only it implements the KV caching, but it also optimizes it even more in 2 ways. The first one is using the paged KV caching. The traditional KV caching, which is non-continuous, uses non-continuous memory space. Once we store the keys and values in some block in memory, it's going to occupy the entire block. So we can't use the block anymore. In page KV caching, what we do is that we take the keys and values matrices and we chunk them, and we store them in a more flexible way using lookup tables and using a continuous memory space. The second thing is using quantized solution, which it takes the parameters of the keys and values, and it changes the precision of it to a lower precision, which eventually requires less space and less computation. So once we combine these 2 things, we get an improvement in the performance of the model. NIM also supports something which is called KV cache reusage, which is the ability to load from the cache the keys and values of prior sessions. So there is a user which talks with the chatbot, and it talks with him in one session and then the day after in another session. We want the information from the previous sessions to be stored and be used in the current session, but we don't want to recompute it every time. So instead, what we do is that we save it into cache and we load it. And this improves the TTFT because the user received the first token as fast as possible. Now, you can see that this is relevant for each user individually. So we need to do it for each user individually. But the thing is that there are also some other things like the system prompt, which tells globally for the LLM for all of the users how to act, what to do, what to answer, what to not to answer. And this can also be cached in memory and used, so the user will receive the answer as fast as possible. Another cool thing is tool using or tool calling, which is the ability to tell the LLM, listen, I have more tools that you can use. These tools come in the form of functions with name, description, input variables, output variables, and so on. Everything that the LLM needs to be familiar with. And the LLM can use it. Let's see an example. Let's say I have an application on the left, and I have the NIM, the LLM, on the right. And the user asks questions, what's the weather today in Santa Clara? I know in the code that I have some service that can receive the weather from the internet. He only needs to get the location. And the LLM also knows it because I loaded it with the tool calling, and I told him, listen, I have this tool for you. So the LLM tells me, the developer, hey, please call this service. Tell them that I want the Santa Clara weather. We will call the tool itself. We receive the answer, send back to the LLM. And the LLM, using both the original prompt and the answer that we got from the tool, will compose a readable answer and send it back to the user. NVIDIA NIM is part of the NVIDIA NIM framework, which is our end-to-end framework for everything related to generative AI, for creating, for training, customization, everything, data preparation using NIM Curator, and more and more and more. For example, we have the NIM Retriever NIMs. Remember that these are microservices. These are mainly used in applications like RAG, Retrieval Augmented Generation, embedding the documents and retrieving the documents and re-ranking the documents, and you can see the improvement. Really huge improvement just by using these microservices. And if we're speaking about RAG, Retrieval Augmented Generation, let's see an example of what it can do. RAG solves the issue where a foundation model, as strong as it can be, it still is not exposed to the data and the documents that I have in my company. And one option is to take the model and fine-tune it and retrain it, but it will require a lot of resources, time, and money. And the second option is to use RAG, which first take the data, and using a few microservices, it cleans the data and embeds the data into a vector database, into a vector space. So there is a vector representation of the data. Then when the user asks a question, the question will flow through the NIM re-ranker and the NIM retriever, and it will compare the vectors, and it will try to find which chunks of information, which data from my own data can answer the user's question. It will retrieve this data, will re-rank it in order to keep only what's important, and give it all to the LLM. And the LLM will combine everything together and give us a more accurate answer. NIM also gives a solution of blueprints, which are workflows in specific use cases that shows how to use the different microservices, how they connect to each other. You can basically download them, use them, change them to your needs. Let's take, for example, the multimodal PDF data extraction. In this case, we take the documents and we parse them using different NIMs in different formats, as images, as charts, as tables, just as text and the metadata. And after cleaning, like I said before, we embed it into the vector space and we use it in RAG. NIM also supports PEFT, which is a parameter efficient fine-tuning like LoRa, lower rank adoption. This is another solution in order to train the model without fine-tuning everything. We just train an adapter, which affects the weights of the model. And we can train it to different tasks. We can see here that there are 3 tasks, a request for internal query, for code generation, for customer support. Each of them is different. but we still want to use one single model. So the single model is in memory, but when the user sends a request, we want him to take the relevant adapter, pull it into memory, and use it with the already not running NIM in order to provide the best answer possible. And what NIM does, and the NIM framework, it supports the training of this LoRa, or just taking it from Hugging Face if you have a LoRa that you want to use and just put it in the adapter store and that's it. So NIM is part of the NVIDIA AI Enterprise, which is a paid subscription. And when you deploy it, you basically need this subscription. But lucky for us, there is a free access if you have an NVIDIA developer account and if you just generate the API. So you can start just playing with it, downloading it, and that's it. There is also the NVIDIA AI Workbench, which is another tool, like a one-click deployment tool that allows you to run it on different operating systems, workstation, data centers, clouds, remotely, whatever you want, with also some points from before. And that's it. If you want, you can scan this QR code in order to receive for the next 24 hours a free self-paced course out of our NVIDIA DLI. Please use it, and then you have 6 months in order to complete it. And thank you very much. That's my LinkedIn if you want to connect.